we begin this lecture by observing the relation between the transfer function and the impulse response of a circuit. Now, let's quickly remember what impulse response was. Impulse response of a circuit was the zero state response of that circuit when the input was a unit impulse applied at t equals 0. Okay, so let's see what that implies from the transfer function point of view. Suppose that this is our LTI circuit. Okay, this represents the input, and here we have the output denoted by y. Okay, and for this circuit, the transfer function, which is denoted by h of s, relates the input and output in the following equation. Okay, where h of s transfer function is defined as the ratio of the output transform to the input transform, under the assumption, under the condition that all the initial conditions in our circuit is 0. Okay, now let's try to see what this implies when this input is not an arbitrary input but unit impulse function. Okay, so for the input w of t is the unit impulse function. The corresponding w of s is very simple. Okay, we're talking about the Laplace transform of the delta function, which is just constant 1. Okay, so w of s is 1. So y of s, therefore, the impulse response, or the transform of the impulse response, is h of s times w of s, and w of s is 1. Therefore, y of s equals h of s. So that means if you take the inverse Laplace transform of h of s and obtain h of t, that function, that time domain signal, is no other than the impulse response of your circuit. Okay, so that implies y of s equals h of s times w of s, and w of s is 1. So that implies y of t is the inverse Laplace transform of the transfer function. Okay, therefore inverse Laplace transform of h of s, which we denote by h of t, is the impulse response of the circuit. Okay, so therefore the transfer function is very closely related to the impulse response. It simply is the Laplace transform of the impulse response. Okay, now let's apply our discovery to an example which we already considered in our previous lecture. Okay, now this is the input driving the circuit, and we have the parallel connection, and here the series connection, and we collect the output here between those pairs of terminals as the voltage, plus minus V2, R2, C2, C1, R1. Okay, now we're interested in, and this is V1, the input, but we're interested in the impulse response of the circuit. Therefore, our input is delta t. Okay, so we're trying to now find impulse response. So that means all the initial capacitor voltages are 0, and under that condition, find the response V2 of t, that is the impulse response for the following parameter values. R1 10 kilo ohms, C1 microfarad, R2 12.5 kilo ohms, and the second capacitance is 2 microfarads. Okay. Now, all we have to do is obtain the transfer function. In fact, we already had the transfer function from the previous lecture, so we have to evaluate it for this given set of parameter values. And once we have h of s, all we have to do is find out its inverse Laplace transform, and that which we call h of t will be our impulse response for this example. Okay, here goes the solution. So earlier we obtained the following voltage transfer function from V1 to V2. HV of S, okay, was R1 C1 S plus 1, R2 C2 S plus 1 with the denominator R1 C1 R2 C2 S square plus R1 C1 plus R2 C2 plus R1 C2 S plus 1. Okay. Now, this transfer function for the set of parameter values boils down to the following: 10 to the minus 2s plus 1 times 10 to the minus 2s plus 1 over times 10 to the minus 4s squared plus 5.5 minus 2s plus 1, and multiplying both numerator and denominator by 10,000, we obtained the following final form: 140s plus 4,000 over s squared plus 220s plus 4,000. Now, what we're going to do is we're going to figure out the poles of the we're going to find the poles of the transfer function, or the roots of the denominator polynomial, and then we're going to apply partial fraction expansion and write it as first order terms, and then it's easy to figure out the inverse Laplace transform. We cannot directly write this as first order terms, sum of first order terms, because this is not a strictly proper rational function, okay? Meaning that the order of the denominator polynomial is not strictly larger than the order of the numerator polynomial, okay? So we have to, therefore, perform a polynomial division and write this as something plus a strictly proper rational function. And that something is, what that something is clear. The highest order term is s squared, the highest order term is s squared, and their coefficients are 1. Therefore, this we should be able to write as 1 plus, okay, a strictly proper rational function. So, after that polynomial division, HV of s can be written as 1 minus 80s s squared plus 220s plus 4,000. Okay, and now we can apply partial fraction expansion to this. So this equals over s plus 20 times s plus 200. That equals 1 plus something over s plus 20 plus something over s plus 200. This is 8 over 9, and this is minus 800 over 9. Okay, therefore we all have now simple terms representing the transfer function, and we can compute the inverse Laplace transform, which will give us the impulse response. Okay, so finally h of t, the impulse response, is the inverse Laplace transform of this. So we have 1 in s domain. The corresponding signal in time domain is the impulse, okay, unit impulse delta t. And then we're familiar with these terms also. So that produces 8 over 9 times e to the minus 20t, and the other guy produces minus 800 over 9 times e to the minus 200t volts. Okay, so that's the impulse response for this circuit. Let's also talk about the step response, which should be closely related to impulse response. And since the impulse response is closely related to transfer function, step response should also be closely related to the transfer function. So let's figure out that relation now. Now, this time the input is unit step function, and again, by definition of step response, all the initial conditions are set to 0, so we're talking about a zero state response. And then we look at the output when the input is unit step. Okay, so this is our block diagram representing our circuit, and the relation between input and output is described by the transfer function h of s. W and y are our input and output respectively. So that's our notation. Okay, so we're dealing with the step response, so that means W of t, our input to the circuit, is u of t. Okay, this is unit step. So, to figure out y of s, or to figure out y of t, what we do is we can figure out y of s, and we can take the inverse Laplace transform. And what's y of s? Y of s is h of s times w of s. And what's w of s for this particular input? It's 1 over s. Okay. So, w of t is ut, that produces w of s equals the Laplace transform of unit step, which we know equals 1 over s. Okay, so that means the output, or the transform of the output when the input is unit step, is h of s times w of s, and w of s is 1 over s. Okay, hence unit step, or the step response is the inverse Laplace transform of transfer function divided by s. Okay, therefore y step, so let this be the step response notation. Y step t is inverse Laplace transform of h of s over s. Okay, so impulse responses, inverse Laplace transform of h of s. Step responses, inverse Laplace transform of h of s over s. So this is the step response. Okay. We also remember from our S-domain review that whenever we have such a form, the the signal in the corresponding signal in time domain simply is the integral of what's being divided by s. Okay, integral of the inverse Laplace transform of h of s. So therefore, inverse Laplace transform of h of s over s is the integral of h of t, which is the impulse response. So equivalently, the step response can be expressed also in terms of the following integral: 0 inverse to t h tau d tau. Okay, where h of t is the impulse response. Okay. Where h of t is the impulse response. Okay. Now let's also talk about the relation of impulse response and the convolution integral. Impulse response and the operation known as convolution. Okay, now consider the following scenario. Suppose that we're given or somehow computed impulse response. Okay, of our system, of our circuit h of t. And what we're interested in is the response of our system to some particular input. Okay, input w of t. So that means what we want is, given this information h of t, what we want is the response or the zero state response of our circuit to this arbitrary input w of t. Zero state response y of t when the driving force is w of t. Okay, let's say we have the impulse response and we want to figure out the response for, let's say, a sinusoidal signal. W of t equals some cosine omega t, let's say. Now, we know that h of s, the transfer function, is the Laplace transform of the impulse response. Okay, so this is our transfer function. And W of s is the Laplace transform of the input for which we want to figure out the response. Okay, so in S domain, therefore, we can write y of s equals h of s times w of s. Okay, and in time domain, y of s equals the inverse Laplace transform of this product, h of s, w of s. Okay. Now, one way to compute this is, well, this inverse Laplace transform is figure out this h of s times w of s, and then doing partial fraction expansion and looking at the Laplace transformation tables, we can figure out y of t. Or there's another way, an operation called convolution integral, which we can compute y of t using these two time domain signals, okay, without ever computing h of s and w of s, okay, because product in s domain corresponds to convolution in time domain. Okay, so this can be also computed as the following: integral h t minus tau w tau d tau. And the notation for this convolution integral is h star w. Okay, so this is called convolution integral. Okay, now let's consider a simple example where we compute the response, okay, y of t, both using, let's say, partial fraction expansion and also directly in time domain by performing this integration, and verify that at least for that simple example this equality holds. Okay, here is our example. Suppose that the impulse response of a circuit is 200 e to the minus 100 t ut. Okay, so it's clear what the transfer function is. It's 200 over s plus 100. And for this impulse response, find the ramp response okay, y of t when all the initial conditions are set to 0, and from the input we apply unit ramp, namely w of t is t times ut. Okay, a function that climbs with a constant slope of 1. Okay, so let's use both ways. We can go to S domain, or we can perform everything in time domain. So let's do it both ways. What's h of s for the given impulse response? It's clear that it's 200 over s plus 100. H of s is the Laplace transform of 200 e to the minus 100t, which is 200 over s plus 100. And what's the Laplace transform of unit ramp? It's Laplace transform of t. Okay, so that's the integral of unit step. And when you integrate, what you do is you divide by s in s domain. So 1 over s divided by s, so that produces 1 over s squared. So that's 1 over s squared. Okay, h of s is here, w of s is here, therefore their product gives us y of s. And then by inverse Laplace transforming that expression, we can obtain y of t. That's what we will do. Okay, now here we have y of s equals the product s plus 100 times 1 over s squared. Okay, so that means y of s can be written as, so we have a pole at minus 100 and we have a double pole at 0. So that means y of s can be written as sum of three terms: k1 0 over s squared plus k1 1 over s and plus k2 over s plus 100. Okay, and these residues can be computed to equal 2 over s squared plus minus 1 over 50 s and plus 1 over 50 over s plus 100. Okay, and then it's easy to write down what y of t is. Y of t equals, this produces a ramp, this produces a step or constant function, and that produces an e to the minus 100t term. So that means y of t equals 2t minus 1 over 50 and plus 1 over 50 e to the minus 100t for t greater than or equal to 0, or just simply multiply everything by u of t. So that's the unit ramp response, okay, for a circuit whose impulse response is given as that. And now, how we computed y of t? Once again, we transformed everything to Laplace domain. Okay, we figured out the transfer function, we figured out w of s, the transform of the input. We take the product, that's the transform of the output, and then by inverse Laplace transforming that product, we obtained y of t, the ramp response. And now, since this product, inverse Laplace transform of this product, equals the this term, the convolution integral, so that means we should be able to figure out y of t, compute y of t, without ever going into the s domain, by simply performing this convolution integral. So let's do that and see that we obtain the same result. Okay, here is a second equivalent way, or y of t equals this integral from 0 to t, h t minus tau w of tau d tau. Okay, h is given, and the input w of t is also given. So that integral reads from 0 to t 200 e to the minus 100 t minus tau times tau, okay, d tau. Okay, and that can be written as, note that integration is with respect to tau, therefore we can take this e to the minus 100t term outside integration. So let's do that. 200 e to the minus 100t, and then from 0 to t, what remains is e to the plus 100 tau, tau, d tau. Okay, so let's therefore try to figure out this integral, an exponential multiplying a polynomial of degree 1. So that can be computed easily by integration by parts from 0 to t, tau e to the 100 tau d tau equals, okay, so let this be our v, and let this be our du. Okay, so integral of v du is uv, the product uv, minus integral of u dv. Okay, so if this is du, what's u? U is 1 over 100 e to the 100 tau. So that's our v u product. Okay, minus u dv, okay, 1 over 100 e to the 100 tau d tau. Okay, this is our dv, and this is our u. Okay, so what we're doing is we're doing integration by parts. So we have gotten rid of this term, the t term multiplying the exponential, and now in this integral we have just pure exponential, which is easy to compute. Okay, so this produces what? T over 100 e to the 100t. Okay, so that's the first term. And as for the integral, we have minus 1 over 10,000 e to the 100t minus 1 over 10,000. Okay, so this is what we marked with this question mark here. Okay, therefore this times 200 e to the minus 100t should be our y of t. So let's see whether that's the case. Therefore, y of t equals 200 e to the minus 100t times the question mark, and the question mark is computed as here. T over 100 e to the 100t minus 1 over 10,000 e to the 100t plus 1 over 10,000. Okay, that produces 2t minus 1 over 50 plus another 1 over 50 e to the minus 100t for positive times. Okay. Now that the two answers match. Therefore, we could either use the convolution integral without ever going into Laplace domain, or compute the output, the response, using inverse Laplace transform. Okay. Now let's consider the following example. Which will make clear the relation between the transfer function and transfer function that links an input to the output, and the differential equation that links the same pair. Okay, so consider the following circuit. Series RLC circuit. Okay, Vs is our input. We have R, C, IL, this is L, and this is the capacitor voltage, Vc. Okay. Now, the input of the circuit is the voltage provided by the voltage source, and the output, we're told, is the current passing through the inductor, which also is the current that leaves the input, okay, the voltage source. Okay, for this example, we're asked to perform the following: obtain the second order differential equation that describes the input-output relationship, and also obtain the transfer function. And then when we do that and compare the differential equation with the transfer function, we're going to see something quite remarkable. Okay, so let's start with A. So V of S, okay, or excuse me, Vs in time domain, we're in time domain, equals the voltage provided by the input equals the sum of three voltages, okay, plus minus, plus minus, plus minus, the voltage of the resistor plus voltage of the capacitor and the voltage of the inductor. So let's express everything in terms of our output, which is the inductor current. So in terms of the inductor current, the resistor voltages are times IL, and then we have VC, which equals initial capacitor voltage plus the integral, okay, 1 over the capacitance. Then we integrate the capacitor current, but since capacitor and inductor, they are in series, capacitor current is same as inductor current. So what we have here is IL tau d tau, okay? And finally, we have the voltage of the inductor, which is L DIL plus L DIL, okay? Now, to get rid of this initial condition, or this that integral also, what we do is, let's differentiate both sides once again. And in that case, what we have is, okay, this is constant term. After differentiation, it disappears, and we have L d square IL, okay, double differentiating that, plus we have 1 over C times IL, differentiating removes that integration, and finally we have plus RDIL. So let me write the second order term, it's first order term here, RDIL plus 1 over C IL, and that equals the derivative of the input, okay, dVs. And then we can rewrite this equation as d square IL plus R over L DIL plus 1 over LC IL equals 1 over L dVs. So that's the differential equation describing the relation between input and the output, which is the inductor current. So let's call this equation 1. And to obtain the transfer function, let's transform the circuit into S domain. Then we have plus minus Vs SL 1 over SC. This is R, and this is our output IL. Note that because we need that circuit for the transfer function, obtaining transfer function, we don't worry about the initial conditions, because by definition they're 0 for capacitor and inductor. Hence, capacitor and inductor, they are represented only by their impedances. Okay. Now in this circuit, which we know can be treated as an LTI resistive circuit, it's easy to write down what Vs is. Vs equals, okay, the equivalent impedance seen by Vs times the current visiting them. So we have Vs equals R plus 1 over Cs plus Ls times the current IL. And that can be written as LC S square plus RCS plus 1 over Cs times the inductor current IL. Okay? So that immediately gives us the transfer function. In other words, ratio of IL to Vs. It's simply you take this fraction and reverse it. So the transfer function IL over Vs therefore equals over L S S squared plus R over Ls plus 1 over Lc. So that's our transfer function. Okay, now the transfer function, or this equation, allows us to write the following, or in other words, we can rewrite that equation as something times IL equals something times Vs. Okay. So note that this equation, which is the equation from which we extract the transfer function, can be rewritten as the following: s square IL plus r over L s IL plus 1 over LC IL equals 1 over LS Vs. Equation 3. Okay, and now let's compare equations 1 and 3. Now, equation 1 is the differential equation. It's in time domain. And equation 3 is just a way to rewrite the transfer function. Okay. Note that they are the same equation, with the only difference being that here the operator, derivative operator d, we have the derivative operator d. Here instead we have s, our complex variable, and here the variables are lowercase letters, and here we have the capital letters because we are in S domain. Other than that, they are the same equation. So that means if you have the transfer function, or that equation, which is more or less the same thing, from that you can obtain the differential equation, okay, describing the relation between the input and output in time domain, or vice versa. If you have the differential equation, you can easily go to the transfer function representation. And the reason is obvious, because if you have this equation, transform it to transform both sides using Laplace transform. And since we're trying to obtain the transfer function, by definition, all the initial conditions are 0. When that's the case, it's really easy to obtain the differential, the Laplace transform of the derivative operator. All you have to do is, whenever you have a differentiation or operator d, replace it with s, okay? And you don't have to worry about the initial conditions. They're all set to 0. And when you do that, you automatically obtain this equation, or in other words, the transfer function.